So now today, I'm going to go into another very important technique about equivariant cohomology. And it's called the GKM description or GKM technique or GKM theory for the torus actions on the manifold. And in our case, Hamiltonian torus actions. And sometimes this technique can be used to calculate equivariant cohomology. But in our case, we already calculated equivariant cohomology. So what's the point, right? So the way we computed equivariant cohomology was writing the cohomology ring as a quotient of a polynomial ring by some relations, right? But this GKM description will give you another presentation of an equivariant cohomology as a subring of direct sum of a polynomial ring. So sometimes people call it this quotient ring description as a presentation of a ring, and this presentation as a subring of direct sum of the polynomial ring, that was called a co-presentation. Right? It's just a different way of describing the ring, and each of these descriptions have a different good side and bad side. So the goal of this introducing GKM description is we haven't really understand the geometric meaning of those parameters in this equivariant cohomology, or how it descends to a class in the ordinary cohomology and what does it represent geometrically. And those things using these descriptions I will be able to explain. So for example, in the Professor Cho's talk or yesterday's talk too, the divisor class, right? Divisor class was generating cohomology of toric manifold, but where is it in this Stanley-Reisner ring or the quotient of the Stanley-Reisner ring? And that actually corresponds to those xi's. Yeah? And then the goal of today, hopefully, to explain how this divisor class corresponds to those xi's. And then I can prove that using this description. Yeah? That'd be great. Right, so behind this GKM description, there is a very important theorems. And this theorem, sometimes it's called the Injectivity Theorem. And also, it's the first time I think the Chan and Sherba showed in more general setup. And the spelling is very awful. No, it's not awful, but it's hard to pronounce. But it's called a Chan-Shelbrett lemma. And those things are elaborated in the paper by Goreski, Katwitz, McPherson's paper to describe the cohomology ring of torus actions on not only the symplectic manifold but the algebraic varieties. Yeah? So this presentation of this theorem is due to Tomoo and Weizen and all the proof in terms of Hamiltonian torus actions that are provided in those papers by Tomoo and Weizmann. So what does it say? So M, again, it's connected, closed. Closed means compact and without boundary. A closed manifold with Hamiltonian. So today, we already seen that there are too many torus, right? And that was really confusing. There's G and T and R, and you have to be careful when you talk about equivariant cohomology with respect to which action for which space. Right? Are you talking about the quotient by this G action or before you take a quotient? So it's very confusing, but what can I do? I mean, that actually, this sort of transition between taking R equivariant, taking a T equivariant, this transition is very subtle, but it's very important. Yeah? And you have to be sort of free to go back and forth between those different equivariant cohomology. But the point is they are the same. Yeah? But anyway, so in this case, just to apply this in the toric context, I'm going to use R action here. Yeah? So M is going to be the toric manifold, right? The toric manifold was moment angle complex modulo G. Okay? So you can take R equivariant cohomology of this, and that's going to be actually T equivariant cohomology of the C delta. But anyway, so that I'll be explain those things in more explicit example. But let's start with Hamiltonian torus R action on the connected closed symplectic manifold. Right? And then the player R is torus. Yeah. So again, you should keep this short exact sequence in your mind. Yeah? And this is, here you have a B and here have A. Yeah. Okay, so the players of this GChem theory is, the main player is fixed points. So basically this GChem description is writing all the data about this M, which is the equivariant cohomology, in terms of the data around the fixed points. So the amazing thing about this Hamiltonian R action with the isolated fixed points or some fixed points is that a lot of information about this R action on M is encoded only around the fixed point. So you only need to look at what's happening around the fixed points, and then you can tell a lot of things globally. Yeah? So it's kind of a localization technique, and it has to do with this famous localization theorem of group actions, which I hope to explain at the end of the lecture, but probably not. But it's in the last chapter of the lecture notes, so you can actually learn that on your own. All right, so this is the fixed points. Right? In the toric case, those are just the finite number of points in M, which corresponds to the vertices of the polytope, right? So fixed point, which is a set of zero-dimensional orbits. Yeah, R orbit. Yeah, and in this particular GChem theory, there's another very important player, which is a set of one-dimensional orbits. So suppose this M1 circle, that's a set of one-dimensional orbits, R orbits. Okay, and the reason why I put circle is I actually want to close it. So M1 is the closure of this one-dimensional orbit, and because of Professor Lehrman's talk, when you take a closure of one-dimensional orbits, it actually a union of one-dimensional orbits and zero-dimensional orbits. It's kind of the slice theorem localization, local normal form around the fixed points and this one-dimensional orbits. Yeah. Okay. Sorry. This I should write MR. Okay. And then the diagram, I'm interested in this. So M, yeah, the original manifold, and there is inclusion of the fixed points. It's called I. Yeah. And then there is this M1. Yeah. M1 is the union of one-dimensional orbits and zero-dimensional orbits. So the fixed points includes to this one-dimensional orbits closure. And this one actually called one skeleton. Yeah. Okay, so the fixed point goes into one skeleton as an inclusion, and let's call it J. Okay, and we're interested in cohomology, so take equivariant cohomology. So you have R equivariant cohomology of M, and the pullback I star, the R equivariant cohomology of MR, and then here R equivariant cohomology of one skeleton. Okay, it's the pullback by J. Yeah. All right. So the content of this theorem is, so first let's just write when you use Q coefficients. Yeah, there's some subtlety between the integer coefficients and rational number coefficients. Q coefficients, life is easy. One, this I upper star, the pullback is injective. Right? So that's the injectivity part of this theorem. Right? And what does this say? Right? Somehow this was a technique to understand R equivariant cohomology of M. And this is injective into R equivariant cohomology of fixed points. And what is this R equivariant cohomology of fixed points? So by definition, this was cohomology of the Borel space. Right? But R acts on fixed points trivially. So this is canonically isomorphic to BR cross MR. Right? R doesn't act on the fixed point, so it's just the classifying space cross fixed points. So the Kuhn formula you apply, this is equal to H of BR, which is the polynomial ring, and so yeah, it cross the cohomology of the fixed points, right? So the more often we assume that Toric case, for example, the fixed points are isolated points. So this is just a bunch of direct sum of the zeroth cohomology, like a higher cohomology disappears. So it's this. So the isolated case, isolated fixed point, this is just a direct sum over the fixed points of bunch of polynomials. Yeah? Or Q. Yeah? So basically, we want to have this, we want to understand this equivalent, our equivalent cohomology of M, but that's going to be subring of bunch of polynomial ring, right? Direct sum of polynomial ring. So this is somehow kind of, it gives you some nice presentation. That's all what it says, right? So this injectivity part is saying that you can present, you should be able to present this ring as a subring of direct sum of polynomial ring, which sounds great. Right? But then, I star, yeah. This is injective. That's the one of the content of this theorem. Okay? But then, okay, I know that this thing sits inside of this direct sum of polynomial ring, but how do we calculate? Yeah? I mean, if we can't calculate the image of this injective map, it's useless. So this theorem comes with a way to compute the image of this equivalent cohomology. Okay? So the second player of this theorem is this one skeleton. Right? The image of I is computed by image of J. Right? So is it more helpful if you can calculate the image of this? It's easier than calculating the image of equivalent cohomology of M. Yeah? And it's actually happened to be very easy, in particular an isolated case. You know, because like you're throwing away all higher dimensional orbits, right? So often this one skeleton has very easy description. I mean, not this cohomology of M1 itself, but the image is going to be very combinatorially easy to describe. Yeah? Right, so that happens, this is the easy life case. Over Q, everything is go good. But then often you want to make sure that things work okay over Z coefficients. And then you have to put some conditions. 1 and 2 holds if following condition, say Z condition, holds. Yeah? Okay, so the condition says take any connected component of the fixed point set, connected component. Yeah? So in the isolated case, we just pick a point in MR. Right? And then you look at the representation of the torus on the tangent bundle. Yeah? So I don't care about the direction of F. So if F is positive dimensional, there is this direction where torus acts trivially. Right? So let's look at the normal bundle. Normal bundle of F, which is tangent bundle of M restricted to F divided by tangent bundle of F. Right? And here there is action of R. Okay? So it's an equivalent bundle over F with R action. Right? And it decomposes into the eigenbundles. Right? You look at each tangent, each tangent space, you decompose into irreducible representation of this R, and it gives you decomposition of this bundle into eigenbundle. So let's call this, say, I start from 1 to a codimension f modulo 2. Right? So the rank of the normal bundle is basically codimension of f inside of M. Right? And then if you decompose into irreducible representation, then each irreducible representation is 2 dimension. So you can decompose into this number of one-dimensional representation, say C of lambda I. So here lambda I is a weight, so it's inside of the weight lattice. Okay? So I haven't set any condition here yet. The condition is lambda I is primitive. So recall, primitive means that it's the shortest integral vector. Right? This is a lattice, and this lambda I has to be shortest integral vector. Yeah? So why this condition has to be satisfied to prove this theorem? I mean, how do we prove this kind of theorem? I mean, I think if I have like another extra hour of proving this theorem, it's actually very pretty proof. So the very important piece of geometry we use is basically the fact that the moment map gives you more spot function. Yeah? The moment map is great. It gives you families of more spot functions. And if you choose a nice one, a generic one actually, then right. So there is some lemma called Atiyah-Bhatt lemma, but then I don't think I can mention that right now. But anyway, so we heavily using the fact that the moment map gives you a lot of most spot function, and most spot function gives you some kind of decomposition in decomposition of manifold along the critical sets. And if you take a generic most spot function from a moment map, those critical set becomes exactly the fixed points. Yeah? So basically, this most spot function coming from moment map, generically, it decomposes manifold into, you have the bottom critical sets, which is sum of the fixed point set, and then you have a part of the normal bundle going this way, and then you have another critical point here and going this way. So somehow you're ordering the most spot function order those fixed points from bottom to top, and then this somehow decomposes manifold in sort of cells, right? So the way we prove this kind of injectivity first is that you can use some induction on the number of critical points. So here you take something here and you look at the fixed point, it's injective, and then using that on the second level, everything below you look at, and fixed point set gives you inclusion in a pullback. So that kind of induction is operated by taking a single most spot function which gives you critical sets as a fixed point. Yeah? So that's basically what happens in the paper by Tomoo and Weizmann. Yeah? Right, but our goal is really make a use of this theorem so that we can actually calculate a lot of things. Okay, so so I should put some example. Like everybody loves basic example of Hamiltonian torus action as S1 action on CP1, right? S1 action on, maybe I should say U1 action on CP1, right? Right, so let's just fix the action here. So t acts on this homogeneous coordinate by x, ty, which is the same as t inverse x, y. Yeah? And let's say, so what are the fixed points? Fixed points are, say, P1, let's say 1 and 0. Right? This is a fixed point. Say this is a North Pole. And there is P2 and 0, 1. Okay? So what does this theorem says? It's kind of trivial. You have this U1 maybe I should use R already, right? This is R. So R, equivalent cohomology of CP1. You pull back to the fixed point, equivalent cohomology of P1, direct sum equivalent cohomology of P2, which is just Z of U1, direct sum, no, the U is the canonical generator of the weight lattice. Weight lattice is just the one-dimensional, right? And U corresponds to the identity character of R. Yeah, the canonical generator of weight lattice. If you identify this R star Z as Z, then this is just 1. Yeah. But anyway, as a generator of the polynomial ring, I want to use U, right? Okay, and is this injective? Right? So I want to use this theorem, like over Z, how can I say it's injective? You just need to check the weights on the tangent bundle of the fixed points, right? So I guess TP1 of CP1 is C of minus U. No, it's actually U, right? Yeah? I think it's okay. I think you can look at these fixed points and what's the variation around this P1. You can change this 0 into some numbers. So the tangent direction is given by a y direction. Yeah? So on the y direction, T acts by U. So I'm always confused because there's this tautological bundle and there's a tangent bundle, and I think tautological bundle is a cotangent bundle of P1. Yeah? No? Okay. So I think I calculated tautological bundle weights here. Well, we'll see. I always get confused. C of minus U. Maybe you can help me here.
So here you use the same element and H equal P1 I P2.
P1 and P2, 1, 0 and 0, 1. Here?
You use same element U and U.
Yeah. So the U, so this is basically, because the R acts on P1 trivially, this is basically BR. Right? And here also R acts on P2 trivially, so H of BR.
Just maybe you should have different notation for the generator. You have two different generators. One.
No, it doesn't have different generator. It's the same generator. It's just that it's indexed by P1 and here it's P2.
Oh, so why don't you write that U sub P1 and U sub P2? Or U sub 1 and U sub 2? In that formula up there.
Instead of the
U sub P2.
You sub Z of
This U?
Yeah, could you give me indices? 1 and 2?
No, I don't. It's just the direct sum of polynomial ring. So the element here is F1 and F2, such that A1 and F2 is in Z of U. I will never write that with in indices of Z because U is the canonical generator of the R dual Z. Yeah?
Yeah, but also in polynomial rings you usually use X and Y, not X and X.
But this is not the polynomial ring.
It is a polynomial ring to variables, isn't it?
No. You're confused with tensor products. This tensor product is going to be very confusing because if you write U, it's not U squared, right? So usually you put U1 and U2 so that U1, U2 is U1 times U2. Yeah. So direct sum and tensor products are different. Okay. So probably I haven't really been careful in my computation. I just wanted to say that the weights are plus minus U. Do you agree? So we can agree on that. So at least injectivity applies. Yeah. So here you have injected. Okay. And so now the claim, and probably I'll just make this as an exercise. Yeah, and the proof is written in my lecture notes, so like if you got stuck, you can look at it. But I'll give you some hint for the statement. But before that, I'll give you a statement. Right. So the image of I star is going to be the pair of polynomial in U variable such that U divides F minus F2. Yeah. So actually, I should say this U is going to be it's going to be the weight of the tautological line bundle at P1 and P2, which is going to be plus minus different. So it doesn't matter, right? Plus or minus, but I'll just make sure that this plus U is the weight at P1 and minus U is the weight at P1 for the tautological line bundle. But then I might be messing up the plus minus somewhere. But the claim is this. And so let's just start a little bit, right? The CP1, the cohomology, is generated by first term class of the tautological line bundle. Yep. So L is the tautological line. Right, for each point, you take that line as a fiber of the line bundle. Okay, and this is going to be, as a vector space, it's generated by 1 and the degree 2 first term class of the line bundle. Okay, it's a dimension 2. Yeah, the rank of this cohomology is 2. And this is degree 0, degree 2. Okay, so it doesn't have an odd degree. The equivariant cohomology has this natural presentation. Z of as a module over this polynomial ring. It's freely generated by those bases, 1 plus. Yeah? Okay, and this is basically coming from Relay-Hirsch theorem. Yeah? So this thing, actually you have to think of this as an element in the equivariant cohomology of CP1. So maybe I'll just...
So T is R?
Ah, sorry, yeah, T is R. T is R. Yeah. So here you have CP1 tensor with HOBR going to, this is the isomorphism I'm using here, R equivalent cohomology of CP1. And behind this Riley-Hughes theorem, the fiber bundle is you have ER cross R CP1, and then the base is BR, and the fiber is CP1. Okay, and here let's say it's pi, and here let's call this, I don't know, G. Okay, the Riley-Hughes theorem sends so alpha cross F to a pullback of F, right? F is a class in the base, and you pull back to the total space, right? And then you cup with alpha tilde, and alpha tilde, if you send it by G, pull back, right? So alpha tilde sits in here, and if you pull back by G, it's alpha. Yeah, one of the conditions in Riley-Hughes is that the G pullback is surjective. Yeah, G pullback is surjective. So they should be alpha tilde, lifting of alpha over this point, a total space, right? So basically, in R equivalent cohomology is given by ZU multiplied to 1 plus ZU of first Chern class of the pullback, no, the sum bundle on here, which pulls back to the tautological line bundle. Okay, and this L tilde is given by CP1, well, no, it's given by ER cross R, and R acts on the tautological line bundle, right? And the projection is this. Yeah? And then if you look at this, the inclusion, this is the G, right? And here you have L, and here you have the inclusion, and this is a pullback diagram. Okay? So if you define L tilde as this adjoint bundle, that gives you this property. So that when I have this isomorphism coming from Riley-Hughes, this thing is going to the first Chern class of this L tilde. Okay? Right. So now we know that the image of I star is a free module over ZU generated by 1, 1. Yeah? So here we know that the equivalent cohomology, R equivalent cohomology is generated by 1 and this first Chern class of this L tilde, right, as a free module over this ZU. Okay? So you pull back, you restrict this 1 to the fixed points. Pullback is a ring homomorphism, so it gives you 1, 1. And you have to restrict this line bundle to the fixed points and see what the weights are, right? And that gives you a pair of polynomial. Yeah? So in this direct sum of polynomial ring, this equivalent cohomology sits as a free ZU module generated by this and this. Right? So you can actually calculate what the image is here, very elementary facts about the P1 with the R actions. Yeah? And then look at that description and show that it's exactly this. Yeah? So that's a kind of exercise, right? And then again, it's always easy to get confused by the action and what the weights are. So the plus minus is going to be always messed up. But as long as you're looking at this condition, plus minus doesn't matter. Yeah. Okay.
You have a field result for orbifold?
Oh, here. So I can mention what happens to this theorem for the orbifold. So maybe remark the orbifold case. So I was interested in generalize this theorem, the version of the proof given by Tomoo and Weizmann, what happens to it when we look at the orbifolds, right? So I did that with Tara Holm like maybe 3 years ago, and it's still like on the review. So I could do when this short exact sequence exists, and so T acts on M and G acts on M locally freely, and R action on this is Hamiltonian. Yeah. So in this case, what's the analog of this theorem, right? We need to specify what are those players are in this orbifold setup too. So like philosophically what you have to do is you look at this diagram, right? This is the orbifold, and there's a fixed point, orbifold points, and then there is a one skeleton orbifold analog, one. Yeah? But then for me it's always, I mean, I learned a lot about stack and orbifold and stuff, but it's always hard to do explicit computation, and there are so many things I have to check, but I wanted to be very explicit in a computation and very accessible for the people who haven't really learned the stacks. So like I want to write this thing in the classical geometry. So what I can do is, so this is the whole manifold, right? It's just G equivariant. Yeah? And then what is this, right? So you have, so this fixed point is zero-dimensional orbifold orbit by R action. I don't know what that means here, but that means you take some orbits in M and you kill it by the action of G, and it becomes zero-dimensional. So this should be, there should be some M0. M0 should be dim G orbits in M. Yeah? So the orbits, the G orbit, T, dim G dimensional T orbits. Yeah? That's how I say it, right? So then if you quotient by G action, the quotient becomes zero-dimensional. So this tells you that M0G is a zero-dimensional T R orbit. So you take this M0, so that replaces fixed points. It's just as there is a G action here too. And then there is one skeleton. So this is going to be a dim G plus 1 dimensional T orbit. Yeah? So if you take a quotient by G, then it becomes one-dimensional orbits in orbifold sense, right? But then you have this, the equivariant diagram. So you can do T of M goes into T of M0, and then there's T equivariant cohomology of M1. Yeah? So what's the analog of this diagram in here? So you take R equivariant cohomology of this orbifold, R equivariant cohomology of this orbifold, R equivariant cohomology of this orbifold, that exactly this. Yeah? So now I need to prove this map is injective and this map subject to the image of this.
It's T or
This is T. This is T, yeah. So now I can do a classical differential geometry or symplectic geometry. I don't need to care about the symplectic geometry on the orbifold. It's some kind of pre-symplectic geometry on these manifold, because these are the lifting, like after you quotient, before you quotient. After you take a quotient, you get the symplectic structure on the orbifold. But if you pull up, right, the symplectic structure might not be a symplectic structure. There's some non-degeneracy part, but the non-degeneracy direction is exactly the orbital G. So that's why when you take a quotient, you have a symplectic structure on the orbifold. So you have some two forms on M and M0 and M1. There's also moment map upstairs. It just doesn't have non-degeneracy condition on the two form. But all the techniques used in this injectivity and Chan-Sheldrake lemma done by Tomoo and Weizmann works in this lifting. Yeah? So I could prove everything in this paper by Tomoo and Weizmann and get exactly the same results for this setup. Okay. And that actually gave me a very good perspective, and then you will get some hint of that when I do a little explicit computation for the toric case, toric manifold case even. Any other questions? Okay, so this little computation of U1 action and CP1, and if you apply this GKM technique, you get this description of R equivalent cohomology. It's very combinatorial. You have two polynomials that satisfy some compatibility, divisibility condition, and it's sort of given by the weight. Yeah. Right. So from this, so let me draw a little picture. Right. So you have, say, now to get the GKM description, let's call this the fixed points to be isolated. So you actually have a direct sum of polynomial ring for the equivalent cohomology of fixed points. And then I want to work over z coefficients, so let's assume this. So the weights on TPM, so P is one of the fixed points, isolated fixed points, are primitive. Yeah, that makes sure that the theorem works over Z. And actually, to have a nice picture, I want to assume this. The weights are primitive and pairwise, linearly independent. So somehow the weights are in the direction of the, it sits inside of the weight lattice, right? It's a vector. So the pairwise, if you look at, it goes in a different direction. So it separates the weight, the decomposition of the representation. Yeah, all the representation goes in a different direction. Independent. Yeah. So this condition, what does it say? Right? You have here P. Yeah. And the tangent bundle. Yeah. So you look at this as an inside of M. Right. Here is fixed points, and the tangent bundle decompose into a weight decomposition. And those lambda i's are vectors, but it goes in different directions. So for each, so say this is C of lambda 1, C of lambda 2, C of lambda 3. Let's say 6-dimensional symplectic manifold, so that you have a 3 reducible representation. So there's 3 directions, right? And for each directions, this lambda 1, lambda 2, lambda 2, the torus action is non-trivial. And it's actually better, it's primitive, right? So it's actually like a transitive free circle actions around gives you, so it's a rotation around in this direction, right? So the orbit is a circle, yeah? And then when it gets to, in this vector space, one-dimensional vector space, when it goes to the origin, it goes to the the fixed points, right? So on this side, you have something like this. Yeah? And then there's another fixed point, right? So this goes somewhere, right? And because the manifold is compact, it goes to some fixed points. And there's another P prime, and there is this C lambda 1 prime here. Yeah? And this goes somewhere in another fixed point. Yeah? And so these circles continue to be circle over here, and then when you get to another fixed point, it goes to be closed. So basically what I'm saying is, in each irreducible direction, right, there is this P1 sitting inside of this M. Yeah? And because of the, then on this P1, the whole torus acts with respect to this weight. Yeah? So from that, you can deduce that this lambda 1 prime and this lambda 1, it's connected by this one-dimensional representation. It's going to be inverse to each other. Yeah? So the thing is, for each point you have this irreducible representation, and the weights are all pairwise linearly independent, and you have a bunch of those fixed points, and then you have representations, and those edges are all connected. I don't really... I'm missing something, right? But anyway, there is something over here. So for each those edges, you have P1. I hope this makes sense. Yeah? And those are exactly the picture of one skeleton. Yeah? M1. Yeah? So M1 comes with a bunch of fixed points, and there is some edge corresponding to the weight direction, and on each weight direction corresponding to this edge, there is a P1 inside of M1. So that's exactly the one-dimensional orbits plus the fixed points. Yeah? So it's kind of a combinatorial geometric picture of this one skeleton. And then I want to know the image of this whole thing into the equivariant cohomology of the fixed points. Yeah? And then you just look at each P1, and then you have this. Yeah? But the action, now you have the R action. Right? But our action goes through this U. Right? Lambda I in this picture is a character from R to U1. Yeah? And then U1 acts on CP1. Right? So on this particular P1, R acts through U1. Yeah? And that's specified by this weight lambda I. So what's the image of R equivariant cohomology of this one piece of P1? That will be, there won't be only one use, right? So in this exercise, I should just, if this R is this R and this CP1 is this CP1, and then you have to add U1, UN, U1, UN, right? And then maybe I'll just use red. Yeah, so this R is going to be the big R. Now this claim becomes lambda I. Yeah? Okay. So because all these P1s are connected by just the points, so now finally we have, under this condition, the GKM description is, so you have this M going into the P fixed points. Yeah, and there's a bunch of a polynomial ring. Yeah, the image is, so you have for each fixed point P, you have polynomial. Right? And what are the conditions? For each edge, yeah, it satisfies that condition. So for each edge, say P and P prime, yeah, there's a corresponding weight, right? That corresponds to this weight and then minus of that, right? But so plus minus lambda of P prime divides Fp minus Fp prime. Yeah? And I will explain these weights or these edges in the image of the moment map. It's purely sitting there as like one skeleton, actual one skeleton in the moment map image, so that it's easy to calculate all these weights and the graphs. Yeah? So that's the very powerful tool to describe equivariant cohomology. The description is very combinatorial. It's depicted by the one skeleton in the moment map image, and weights are also calculated by sort of discrete geometrically. Okay. Right, so one last thing. Oh, so maybe I think it's time to do explicit example now, right? How much time do I have? 20 minutes? All right, so hopefully at least I've shown the complete picture of what's happening for CP2 toric manifold, right? Okay, so here it's the standard CP2 polytope. Yeah? And here you have row 1, row 2, and row 3. So the B matrix was 1, 0, 0, 1, minus 1, minus 1. This was row 1, row 2, row 3. Okay, and so this is delta, right? The toric manifold is CP2. Yeah, and so this sits inside of the dual of real algebra R, right? So R acts on here, and I know I set a direction here. The basis of the Z basis of the dual of the Lie algebra U1 and U2. Okay, and then we know how to construct the simplicial complex, right? So here is vertex 1 corresponding to this row 1 facet, and this 2 corresponding to this row 2 facet, and 3, and there is a vertex in the intersection of 1 and 2, here, here, and 2, right? So here you have V of 1, 2, this is V of 2, 3, this is V of 1, 3. Okay, so the moment map, this is the moment map image from the toric manifold, right? And it goes to R2, which is the dual of the Lie algebra. And then you have this V12, V13, V23. Maybe I'll do V12, V1, V23, V13. Yeah? And in the standard homogeneous coordinate, what does this correspond to? 0, 0, 1. Yeah? That's actually because so V12 is the intersection of this row 1 facet and row 2 facet, and that actually gives you the 0 coordinates in the first and second slots, right? Okay, so now this is one picture, and what happens to this injectivity map? So you have the 3 polynomial rings. One, two. So this corresponds to V12, V1, V23, V13. Okay, and so this is Stanley-Reisner ring, right? So there are three facets, x1, x2, x3, and what's the non-facet of this simplicial complex? The only set of facets which doesn't have intersection is the everything, right? So x1, x3, x2, if you intersect, there's nothing in there. So the non-facet is 1, 3, 2. 1, 3, 1, 2, 3 is not in this K delta. Right? So that's the only monomial. So you kill that. x1 times x2 times x3. This is the Stanley-Reisner ring of K delta. Right? So the first question I would like to ask is, this ring is generated by x1, x2, x3. Yeah? And how can I calculate those x1, x2, x3 image in here? Yeah? So then, just to motivate, I'll do, the whole reason why I have this moment-angle complex was sometimes it becomes easier at that level, right? So let's do so this is R equivariant cohomology. Now let's look at the T equivariant cohomology of the moment map complex, moment-angle complex, right? So X was gk delta modulo g. Yeah? And there is a gk delta, which is right, d cross s1, s1 cross d, and d cross s1 cross d. So this corresponds to 1, 2, this corresponds to 3, this corresponds to 1, 3. Yeah? So now let me ask, what are the things in here corresponding to those fixed points? Right? This x is a quotient of this moment-angle complex. So there's some corresponding locus in this description. Right? So this G is actually a diagonal matrix, right? A diagonal torus. So after you kill, it becomes a point. Right? So here you have, this is a disk circle, so you have 0 cross S1. Yeah? And that corresponds to 0, 0, 1. And S1 cross 0 cross 0, 0 cross S1 cross 0. And those are exactly corresponding to V1, V2, 3, V1, 2. Yeah? Okay. All right, so now let's see. Let's denote these things as Z of 1, 2. Yeah? And after you quotient by G, this becomes P1, 2. Yeah? Just introduce some notation. So with respect to this moment-angle complex, it becomes T Z1, 2, T Z2, 3, T Z1, 3. Yeah? And this is supposed to be isomorphic to this, right? But the point is, how do we find those isomorphisms so that we can calculate? But before that, let's just work out this, right? So this is Stanley-Reisner ring, as it is there, right? And what is this? The natural description of this T equivalent cohomology of Z1, 2. Right? So this is 0, 0, S1, right? There's a T action. T is U1 cross U1 cross U1. U1, the first U1 acts trivially, second U1 acts trivially, but the third U1 acts freely, right? So let's introduce T12 is U1 cross U1 cross 1, right, inside of T. Yeah? So this becomes T12 a point. Or maybe I should say H of B T1. Yeah? It's just that the third torus inside of T acts freely, so it's not going to appear in the quotient, Borel space. So it's the same thing for this G3, 2, 3. Yeah? And what is this? Right? So you have this T12 sitting inside of T. Yeah? But if you look at the dual of the Lie algebra, yeah, it's surject, right? And the basis here is U1, U2, no, X1, X2, X3. And when you take a projection, which parameter is going to be killed, right? There is no, the third component in this T12, so this is going to be X1, X2, and X3 is going to be killed. Yeah? So this cohomology, G of X1, X2, X3, modulo X3. Yeah? Yeah? Similarly, so basically this is just X1, X2, okay? And this X2, X3, X1, X3. Yeah? And all this computation is homomorphism over, as a module over this big polynomial ring, right? So in this description, it's easy to calculate what the image of xi is, right? X1 goes to, X1 is not going to be killed in this cohomology ring, so you have X1, right? And in here, X1 is killed, so it's 0. And the third component, it's X1. Yeah? So it's very combinatorial, easy. Yeah? X2, X2, 0, and 0, X3, X3. Yeah? Okay? So now, how can I turn these x's, how can I turn these polynomial ring with two variables here? How can I identify that with all these? You know? So no, this is very linear algebra, right? So say you have T12 here, sitting inside of T. Okay? And then there is this V matrix going to R. This is 3 dimension, this is 2 dimension, this is 2 dimension. Yeah? What do you think about this composition? Hope this is an isomorphism so that you can find a matrix for this 2 torus to torus, and that will give you the coordinate change from X to U. Yeah? So it's easy to do at the level of the dual of the Lie algebra. Yeah. So this is the U space, right? And then there is this B dual, and there is this T dual space. This is X spaces, right? And then you kill some parameter here. Yeah. What was this UI goes here? Yeah, we already did this, right? I mean, it's the dual of the B matrix. So what can you do? You writing U in terms X, X, J, right? J is from 1 to M, right? B is N by M matrix. Yeah? Now, what is this map? Yeah. And this map is you're killing some variable, right? So in this case, we are working in this way. So U1 goes to what? B matrix is here. Right? U1 goes to x1 minus x3. Yeah. And U2 goes to x2 minus x3. Okay? And then U1 goes to, so in this component, you're killing x3 coordinates. So it goes to x1, right? And U2 goes to x2. Yeah? And it seems this is this composition. So basically, when you have this, you're killing some variable, not in the facets. So I could actually write it as J only in sigma Bij xj. Yeah? So sigma stands for a facet of the simplicial complex, which corresponds to the vertex. Yeah? Okay, and this seems to be isomorphic, right, with this explicit computation. U1 goes to x1, U2 goes to x2, and this is generated by x1 and x2. So it's very like trivial isomorphism. Yeah? But why is that? I mean, it's supposed to be something has to do with the B matrix only, right? So let's look at this B12. Right? B12, row 1, row 2. Right? So I'm using this. So each column corresponds to the facets, right? And then I'm looking at the intersection between H1 and H2. And you look at this row 1 and row 2, which is just the identity matrix. Yeah? And that's exactly this map. Yeah? Because you're killing a generator here, which is not in the collection of facets which defines the vertex. Yeah? So you're forgetting certain columns which are not in the facets. Yeah? So this is invertible because the row 1 and row 2 form Z bases. Right? This is the Delzant condition, right? Unimodular condition of the polytope. Yeah? And it happens same for every vertex. That was the condition. For every vertex, you pick a column corresponding to the facets, giving you the vertex, they form a Z basis. So this is invertible over Z values. Right? So I have this X presentation of the image in the fixed points. Right? I want to turn them into U variable. What can you do? You take an inverse of the matrix. Yeah? So in this case, V12 is inverse is going to be the same thing. Yeah? But in general, I define this sigma. So let's take some vertex V, which is given by the I is in a sigma, right? And let's define this as rho I1, rho IN. So the sigma is I1 through IN. Okay? And then you take the B sigma inverse, right? So let's write this way. Rho 1 through rho n. Yeah? and then you multiply lambda 1 through lambda n, you multiply lambda n, rho in, which is identity matrix. So this is the inverse matrix. Yeah? And this lambda I1 through lambda n gives you the image of xi's in the dual of the Lie algebra. So from that computation, we can conclude, so x1 turns into u1, yeah? And 0 is 0, and x1 turns into, so here you have to be careful, right? I only did the computation for the 1, 2 thing. So to do this, what is this? You look at the b of 1, 3, which is 1, 0, minus 1, minus 1. I can't remember this invertible matrix of 2 by 2 matrix. So I think determinant, the inverse, okay, maybe can I cheat a little bit? 1, 0. Yeah. Oh yeah, that's right. Minus 1, 1, and 1, 0.
You have to flip it around and then.
Yeah.
0 on the top.
0 top.
Yeah, switch.
Switch this and this. Really? You flip yeah.
Oh, it's same sign.
I think it's the same, right? Yeah. Okay, so like I'm happy that I'm not the only one. Okay, so this is a 1, minus 1, 0, minus 1. Yeah? So this u minus u2. u1 minus u2. So this is x1, u1 minus. Yeah, great. Yeah. All right. And yeah, so the x2 goes to u2, and x3 goes to 0. Yeah, and x2. Oh, so I have to do all this computation, right? So I will cheat a little bit. But you can do all these computation, right? But I'll give you better way of understanding this inverse matrix, right? But for now, let's just write out the answer. Minus u1 plus u2, 0. And x3, lambda 3 is minus u1. Wait. So minus lambda 2 is minus u1 and 0, and lambda 3 is minus u1 plus u2, and oh, there's minus lambda 3. Wait, I'm confused here. No, I think I'm making a mistake. Okay, minus lambda 1, minus u1. So I think my computation in my notes may be messed up a little bit, but this is what I got. u1 plus minus u1 plus u2 minus plus u1 minus u2. Okay. So I have to look at this matrix, and somehow those lambdas, if you calculate the inverse of this matrix, then it gives you the inverse transformation of this. I think I'm not really making the computation right now, so maybe next time I will make it straight. But the idea is, when you look at this equality, right? And so in this case, you have this V12, and then here you have row 1, here you have row 2, and then you have row 1, row 2 equal this, and lambda 1, lambda 2. Okay, and I want to interpret what these vectors are, right? And because this is the inverse matrix, if you take an inner product with this and this, it gives you 1. Right? If you take an inner product with this and this, again, if you take an inner product with this, well, I should just write it out, right? Yeah, so we have this. Yeah? So can you place what this lambda 1 are in the picture? Right? So lambda 1 is orthogonal to row 2. So that means lambda 1 lies on this facet. Yeah? And then, wait. There's something wrong in here. In here, so the lambda 1 is going to be the, oh God, I'm so confused. Lambda 1 inner product with row 1, that's 1. So that means, oh, finally I so messed up here. Can I stop? I'm so sorry. Like I did, maybe I was so sleepy last night. I promise.